We're going to continue with kinetics today. We've been talking about kinetics quite a bit. Kinetics is the study of reaction rates and the factors that affect them. And your learning goal, Big Idea 4, has been illustrated several times. At this point, you want to be able to write rate equations, solve rate equations, write rate laws from experimental data. So you should have a very high comfort level with all of that. And what we're going to get into today are integrated rate laws. What you've written thus far are derived rate laws. You derive them from the data. Now we're going to do integrated rate laws. Not difficult, some basic concepts you need to know, some comparisons, contrasts you want to be able to make. And I will finalize your assignment sheet and try and get it posted today, but you're looking at a quiz toward the end of this week. We're going to talk about integrated rate laws, and the reason for that is we want to be able to figure out the concentration of a reactant after the reaction has proceeded for some time period. So the question is, what is the concentration of a reactant at a later time if we know its initial concentration? Using integrated rate laws is actually very simple. What's tricky is figuring out when to use an integrated rate law. And the key will be that you'll be given one concentration and asked for a concentration later on, or you'll be given two concentrations and asked to determine either the time elapsed or K, your proportionality constant. So an integrated rate law is an equation. It describes the concentration of reactant as a function of time. Essentially, it's going to express how concentration is in fact time dependent. In a first order reaction, here is your equation. You have ln of the quotient of concentration of reactant at some later time over the initial concentration of reactant A is equal to negative K. K is the proportionality constant we introduced with rate laws, and time. And just watch your units here. K will have some time units to the -1, and if it's in seconds, your time will need to be in seconds as well. So make sure those units jive, otherwise you're not going to get cancellation. Now you can express the integrated rate law for really any type of reaction. We're going to do first order initially, and this is going to be the equation of a straight line. Remember back in middle school you learned about y equals mx plus b format. Y is going to be your y-axis, x will be your x-axis, m is your slope of the line, and b is the y-intercept. So if we apply this here, where basically you know that ln of a quotient is ln of that concentration minus ln of the initial concentration. And now if we manipulate this such that this is the y, we're going to move this to the other side, so we're going to add this to both sides right here. This is our y-intercept, so where it hits is your initial concentration. Your slope is negative K, and you can see that negative slope right here. So if you plot ln of the concentration of a reactant at some time versus time, for a first order reaction you get a straight line with a negative slope. And you should recall, in terms of slopes of lines, I'm sure you remember from middle school that if these are your axes, this would be a positive slope, excuse me, and this would be a negative slope. And if you can't remember, you've got right there, that slope forms the n in negative. So that's your negative slope. That almost looks like a bow tie. Not sure I was going in that direction. But here is your graph. Most importantly, first order reaction. The y-axis will be ln of the concentration at some time t. Where it crosses will be your initial concentration. It varies for 0 order, first order, and second order, and we'll be going through those. I feel that first order will be most important to you, but at the end of this section, right here, I have a table that summarizes the different types of straight line plots. So for zero order, you'll just be plotting concentration. For first order, you'll be plotting ln of the concentration. For second order, you'll be plotting 1 over the concentration. So for first order right here, ln of the concentration versus the time will give you a straight line with a negative slope, and that slope is equal to negative k. All right? Let's take a look at the math. Pretty simple math. Don't foresee a problem with it. This probably will be calculator-based math anytime you get into LNs. You don't have log tables like we did way back in the day. It says the decomp of nitramide is a first-order reaction. That's the first relevant piece of information you've got. Right away, you know that you're dealing with LN. Also, let me point out that on your formula sheet on the back of your periodic table, I gave it to you in purple, they give you the equation for first order. The only thing different here is they didn't give it to you in y equals mx plus b format. You would just move this to the other side. So that would go plus ln of the initial concentration. So there's first order. They give you the second order as well. When we get there, I'll show it to you. And then back to first order. We'll get there in a minute. But right now, that first equation, given. Don't have to memorize it. It tells you that this is the rate law, which you would have known anyway. How would you know that's the rate law? You have first order kinetics, so it's just got to be the reactant raised to the first. You only have one reactant, so it's a gimme. Here's K. And the temperature is important to specify. You need constant temperature. K will be altered. You're starting with, so that's the initial concentration of reactant. And then you want to know at what time will you have that concentration. So that's what we're looking for. Let's get the information down and let's see how we work this, and then there's a second part. And to me, this type of analysis will be pretty straightforward, and if it's first order, it's really easy and a lot of places you can go in. So what you've got here is they tell you first order. They're giving you a K of 5.62 times 10 to the negative third minutes to the negative 1. The initial concentration is 0.105 molar. They want to know the time. 0 for time 0 initial concentration. And they want to know the time it will take to have only 0.0250 molar left. So that's everything given thus far. We know that ln of the concentration at some later time over the initial time is equal to negative kT. They give you that, they subtract the two ln's, but that's the same thing as taking the ln of the quotient. You know how to work division versus multiplication on ln. Questions at this point? What are you solving for? T. How do you solve for T? Divide both sides by negative K. So we have ln of 0.0250 molar over the initial divided by negative K. And it's got to be negative there. You divide it by negative K, and remember that ln of a fraction is negative, so the negative divided by the negative will cancel. So you have 0.025 divided by 0.105, and then you're going to take the ln of that divided by negative 5.62 EE negative 3, and you get a time equal to 255 minutes. Pretty straightforward. Don't foresee any real issue there. And again, when they give you two concentrations and they want to know the K or the T, that's the indication that the integrated rate law will be helpful to you. The other part of the question, you're going to stay with the same information, except they want to know the concentration of reactant at a later time, and that time is going to be 6 hours. Now here's one where I actually do prefer to just do ln of the concentration at the later time minus ln of the concentration initially, that one's not going to change, is equal to negative KT. And now we want to solve for this piece, so we're going to add this to both sides. As such. Are you with me?
Not at all.
Where are you lost?
This part.
Are you not clear on how I move this to the other side? Haley, if I have 3x minus 4 equals 10, how do I get this number to the other
I
side?
get that part.
Okay, so I'm just going to add 4 to both sides, right? That's all I've done so far. But you're going to help me plug everything in to make sure you can follow it. All right, so we're solving for this. Well, we ultimately want to solve for this. We've got the ln built in, but that's easy to get rid of at the end. Maybe I should call this time prime or something so you know it's different than the first. Haley, what's the value of K?
5.62.
Times 10 to the negative 3 minutes to the negative 1. The time, the time that they specify in part B, 6 hours, but this is in minutes to the negative 1, so I've got to get this to minutes, correct? Okay, so that's 360 minutes. And then I'm going to add ln of the initial concentration. What was the initial concentration? 0.105 molar, good. Now just be careful when you multiply and add that, that's the ln of. So I've got negative 5.62 EE negative 3 times 360 equals plus ln of 0.105. So initially I get this. And if I want just the concentration, what do I do? You see, I learned anti-log, but I don't think you did. So you're going to do, I guess it would be the inverse of this, which is e to the x. Okay. So you're going to go from here to here. I learned it as anti-log, but you guys are just going to know it's e to the x. The easiest thing to do is do e to the x of that answer you have that's in your calculator. And you have 0.0139 molar. This is the concentration of substance that remains after 6 hours. And again, the math I think is pretty straightforward, especially for you guys who are in pre-calc and calc. I think the tricky part is knowing what to use when. And like I said, when you have one concentration and you want to know the other at a different time, over a time period, that's when you're going for integrated rate laws. First order reactions, you're dealing with the ln concentration, because what gives first order kinetics in a straight line fashion is the ln of the concentration versus the time. And that's also critically important. You'll probably get some easy question showing a graph where you'd have ln of that reactant concentration versus the time. And where it hits the y-axis is the initial concentration. You might be asked to read things off graphs and apply it, etc., but nothing difficult there. ln of concentration, straight line, negative slope, first order. In most cases, we do deal with concentration, but if you have a reaction where you have just gases, very often you'll look at pressure, so ln of the pressure versus time. You also can do mass only versus time. There's a lot of ways to express it. But what's very interesting in first order kinetics is half-life. And I just want to review half-life with you for a minute, and then we'll link it to first order. So half-life is the time required for half of the original sample to be depleted. So in English, for example, if you started, let's say, with an 100 milligram sample of whatever, the amount of time it takes for half of that sample to be utilized is the half-life. So if it takes 3 minutes to go from 100 to 50 milligrams, that's the half-life. If, for example, I start with 10 milligrams and I get down to 1.25 milligrams and it takes 18 minutes to go from 10 to 1.25, what's the half-life? 6 minutes. And we've gone through 1, 2, 3 half-lives, correct? So that's just some stuff that I'm sure you learned in nuclear chemistry, either in middle school or in honors chemistry, just a little bit with half-life. With a first order reaction, there is a relationship between the half-life, T1 half, the half-life, and K. You can derive this, you don't need to. For example, what you're doing here is you initially had this equation here for first order kinetics. So if you do the half-life and you have ln of a half times that quotient is equal to negative k T1 half, the half-life, you can simplify this as follows and plug in ln of a half. What's ln of 0.5? It's negative 0.693, right? So now you have a negative on both sides. You get rid of the negatives, and you can show for a first order reaction that the half-life is equal to 0.693 over K. So if they give you K, they can give you the half-life. The half-life is a constant that depends only on K, not the concentration of reactant for first order only. Be careful there, first order only. You also can calculate half-life just generically as 1/2 to the n, where n is the total time that's elapsed over the half-life. So if the half-life of a radioactive substance is 2.5 minutes, what fraction of the original substance remains after 10 minutes? So for example, you can do this 2 ways. If you're dealing with fractions, start with 1. You want to know what remains after 10 minutes, and the half-life is 2.5. So that's the first half-life. Here's another half-life. We've gone through 2. I'm sorry. I was thinking backward. Hang on. I think. So what is... I was thinking 10, but we don't have 10. We just have 1. Oops. Let's start again. So let's say you start with 1. What's half of 1? 1/2. 1/2. What's half of a half?
40.
All right, so we've gone through 1, 2 half-lives. How many half-lives do we have to go through to get to 10 minutes?
4.
4. Half of that is? And another half is? So 1/16 will remain after 4 half-lives. Alternatively, we can do this, where we can say 1/2 to the n, where n is the total time, in this case 10 minutes, over the half-life, which is 2.5. What's 10 over 2.5?
4.
And 1/2 to the 4th power is?
1/16.
So you can do it either way. And that's just a little bit with half-life. But most importantly, for a first order reaction only, T1/2 is equal to 0.693 over K. So if they give us K, or we have found it, we can get the half-life and vice versa. And that's what you're going to see in the next problem here. This one is all rolled out for you. We'll walk through it. I really want you to see the linkage. It says in the first order decomp of dinitrogen pentoxide at 335 Kelvin, here's your decomp reaction. If we start with 2.5 grams, that's the initial amount, and then we have 1.5 grams remaining after 109 seconds. What's the value of K? Same first order formula we looked at. Instead of concentration, you can put the mass in directly because it's the same substance. You would divide by molar mass, and you would divide by the same volume, so you're not accomplishing anything by changing it. If we wanted to solve for K, we would divide both sides by -T. That's what's shown here, and here's my K. The next question says, what's the half-life? How do you go from half-life to K? Exactly. So you can use this formula right here. You just got the K. You'd plug it in, and you could get your half-life out. So half-life is 0.693 over K. Here's the K we got over here. And this is your half-life. So if you have K, you can get half-life. And then this problem is more of what you did previously, and I'll let you look at it separately. Here's the bottom line. If you look at the decomposition of dinitrogen pentoxide, if you look at ln of that concentration versus time, there are several things that you can see here that shows its first order. Looking at either here or here, how do you know it's first order? Right here, how can you tell it's first order?
It's a straight line.
Straight line when you plot the ln of the concentration, a straight line with a negative slope. The other thing you want to look at is if you can see consistent intervals, so you know you're going by 50 and then by 50 and then by 100. So from here to here and here to here, you jumped 50 seconds each time. And if you compare the difference between this interval with the difference of this one right here, they're going to be pretty close to the same. You're going to have about 0.35, give or take. And you've got the same thing from here to here and here to here. Now you're going to go 100 seconds, and you should see a consistent interval here about 0.7, about 0.7, about 0.7. That further suggests first order kinetics because you plotted the ln of the concentration. So those are all things you would look at. Now if you plotted just the concentration versus the time, would you get a straight line? No, you're going to get a curved line, and that's something else you want to be aware of, and we'll come back to that in just a minute. With zero order reactions, what you're looking for here, again, the reaction rate does not depend on concentration of reactants in any regard, because if you have a zero order reaction, let's say that you had A plus B yields C plus D, your rate law would be rate is equal to K, A to the 0, and B to the 0. What's anything to the 0 power? So you'd have rate is equal to K as your rate law. As you alter these two concentrations, is the rate affected? Not at all. All right? So if you have zero order, for example, like you do with the decomposition of ammonia, this would be to the 0 power, and as a result, rate is just equal to K. So what gives straight line kinetics here is a graph of concentration versus time only. That's what you're seeing here. Not ln, just concentration. Again, the slope will be negative K. So for zero order, it's concentration. For first order, it is ln of concentration. In your second order reactions, it's a little bit different. Let's say, for example, you were synthesizing nitrogen dioxide and oxygen from nitrogen monoxide and ozone. Here's your rate law, second order. Here, your integrated rate law looks something like this. 1 over the concentration at a later time is equal to positive KT plus 1 over concentration initially. So here what's going to yield a straight line on your y-axis will be 1 over the concentration. The math gets a little bit cranky here. You usually don't see second order with integrated rate law, so I wouldn't stress over it all that much. What you tend to see more of is an analysis of the graphs. It says if it takes 55 seconds for the concentration of A to fall to 0.40 molar, that's the concentration at a later time, from the initial concentration, here's your rate law. We want to know K. So you are going to manipulate this to solve for K. So what you're looking at here, I'll show you that on paper. That's going to be way too hard to follow. You have 1 over the concentration of A at some time is equal to KT plus 1 over the concentration initially. And now if you want to solve for K, you're going to subtract this from both sides. So you're going to have 1 over this minus 1 over this. And that's going to be equal to K, and I'll divide by T at the same time. And manipulating variables in equations is not an issue for you. Shown here, you're just going to plug and solve. Also, one thing you want to make sure you know is units of K. Remember, is molarity 1 minus overall order time to the -1. So be comfortable with that. So if you had second order, as you do here, what would be your units of K? M to the -1, time to the -1. If they specify time, use it. In this case, it would have been seconds to the -1. And then what I especially want you to see is here, and then we'll work through a recent AP problem. So what you've got here is, here are two plots. The first one shows ln of concentration of butane versus time, and this one shows 1 over the concentration versus time. How do you know that this isn't first order?
Slope is positive.
How do you know that when you're trying to figure out the rate law using butane C4H6 as a reactant, how do you know that the kinetics isn't first order? Because you have a curved line when you plot the ln of the concentration versus time. How do you know it's how do you know it's not first order but rather second order?
Because it's 1 over.
Because that one shows straight line kinetics when you plot 1 over the concentration, and that's an important concept to understand. Okay? This is a problem from the 2012 AP exam. It's a piece of a problem. The first part of the problem dealt with thermo. But let's just focus on the second part of it here. It says an experiment is carried out to measure the rate of the reaction, which is first order. First order, first order. Right away with your formula sheet, you know first order, because it has ln. Second order, because it has 1 over concentration, and you only have to know half-life with first order. So that's first order, first, second, first. First order, key piece of information. It says a 4.70 times 10 to the -3 mole sample of ethylamine is placed in a previously evacuated 2.00 liter container at 773 Kelvin. After 20 minutes, the concentration of reactant is found to be 3.60 times 10 to the -4 molar. First thing they want you to do is calculate the rate constant. That's the proportionality constant K for the reaction at 773. Include units with your answer. Let's get the information down and see if we can get this one to rip. They tell you first order. They tell you that you have 4.70 times 10 to the -3 moles of ethylamine. They tell you the volume is 2 liters. At a later time, the concentration of ethylamine is 3.60 times 10 to the -4 molar, and that later time is 20 minutes. First thing they want to know in D, as I said, parts of this question are missing, is the rate constant. What do we do? You know it's first order, so if you don't know where to start, you've got an equation there that you're going to go with. You know you have ln of the concentration of reactant at some time t over the initial concentration. And that's going to be equal to -K times T. We want to solve for K. We're going to divide both sides by -T. we have this. What's the initial concentration? How do we get the initial concentration? You better divide that, right? So that's your K. Yes? So that's your K. And then E asks for the initial rate. And they want it in molar per minute. So how do you get the initial rate? Rate law is K times what? Reactant raised to what power? First, because it's first order, and it says initial, so you're going with the initial concentration. Do you have K? Sam, is something wrong? Are you good?
Yeah, my arm is out.
Okay. And again, nothing is difficult, it's just recognizing what they're asking for. Once you're sure what they're asking for, you can apply all the formulas. This is the derived rate law that you learned at the beginning of the chapter. And then the last question is very straightforward. Just make sure you understand what they're asking. It says, if 1 over the concentration is plotted versus time for this reaction, would the plot result in a straight line or would it result in a curve? Explain your reasoning. So it would result in a curve because 1 over the concentration versus time is for what order? Second order. So the only way you could get first order is if you plotted ln of the concentration versus time. So be careful there. Alrighty? And then the other thing that's in your notes here is highlighted in yellow is what I felt would be most relevant for you to know. Absolutely want to know the straight line plots. The only slope that's positive is second order in this regard. I didn't highlight this, but you absolutely want to know units of K. That's a must. Here's the half-life for first order only. That's given. So this is given, and these two are given in terms of formulas. And from those formulas, you can go back. You'd have no trouble doing plotting. And in a multiple choice format, it might have indicated here, if you had this rate law, it might have said, I'm just simplifying this because it's not going to fit. Which of the following graphs best illustrates this type of reaction? And it would be that, because you need ln of. Alrighty? Definitely want to be comfortable with this graphing piece. That's something that's commonly asked. So at this point in your chapter, you want to be comfortable with rate equations. That's the -1 over the coefficient, blah, 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 blah. The derived rate laws that we talked about the other day, we still have several minutes, it's a regular day. And now you want to make sure you're comfortable with integrated rate laws. I highly recommend a couple of math problems with integrated rate laws, and I definitely recommend that you can do the graphical piece. The only thing we haven't covered thus far is collision theory and reaction mechanisms, both of which we will cover on Tuesday, which is tomorrow. And then you're looking at a quiz on Thursday with a lab on Thursday as well. The lab is short, but it illustrates a lot of good concepts, so I like it. If you haven't done any kinetics homework between now and tomorrow, I highly recommend that you get very busy. Alrighty?